All right, so let's pick up with section 13.6, the electric field of a dipole. And what we're going to be doing a lot of in this class is deriving equations so we can understand where they come from. Once you derive it and you have a simpler version, then you're allowed to use it, but you must first earn the right to use a simpler equation. So we know matter is composed of both positive and negative charges. And when you have neutral matter, so in other words, you would get a net neutral charge, it's either uncharged matter, like neutrons, or you have an equal number of positives and negatives, giving you a net charge of 0. And what we'll see is that you can still have an electric field even with neutral matter because there are still positive and negative charges. So the simplest piece of neutral matter is a dipole. And so this is where you have a negative and a positive charge separated by some distance s. Sometimes s is denoted as d, depending on the textbook that you're using. And since most of you have taken chemistry, we know that dipoles exist everywhere in nature. All right, so we are going to use the superposition principle to calculate the electric field. All right, so there's two ways that we're going to calculate this. We're going to calculate on axis or parallel, and off axis or perpendicular. So we're going to start off with along the axis. All right, so we have a dipole here. So we have minus Q and positive Q, and then we're going to look at the electric field at position A. Okay, so let's take a look at this. So we're going to have for the superposition principle, we're going to have the R minus vector, which will go from here to here. Then we're going to have our positive vector from the positive charge. And each one of these will, of course, contribute a field. So a minus charge is going to point towards the charge. So we're going to have a smaller electric field from the negative charge, and the positive charge is closer. So we're going to have another electric field that's a little bit larger at this location, pointing away from the positive charge. Now, to set up this problem, we're going to say that that the middle of the dipole is at 0, 0, 0. The separation, of course, is s, and we're going to say that our location is at x, 0, 0. So we're going to use some actual coordinate points, and then we'll generalize at the end. So s is going to be the distance between the dipole particles. And as this is a dipole, we know that the magnitude of minus Q is going to be equal to the magnitude of positive Q. Now, setting up this picture is really important. So by this picture alone, we can see that if we were to look at the net field, so let me go ahead and draw the net field. Here, it's going to be pointing in the right direction because the positive charge is closer. And we can also get a sense of what the setup is going to look like. So drawing pictures in Physics 2 is really important. You can learn a lot of information just from drawing an image before you even make a single calculation. Okay, so to go ahead and do this derivation, we need to find r positive and r vector negative, and then use them to find the electric field positive and the electric field negative, and then sum them together. So that is the basis of the superposition principle. All right, so let's go ahead and get started. So if we recall, r is the vector between the source and the observation. So r is equal to observation minus the source. So r positive is equal to x 0, 0 minus s over 2, 0, 0. So if the center of our dipole is at the origin, then we can see that this would be at location plus half of s. Okay, so r plus is equal to x minus s over 2, 0, 0. Now we need to find the magnitude of r plus. So this is going to be equal to the square root of x minus s over 2 quantity squared plus 0 squared plus 0 squared is equal to x minus s over 2. Okay, so chugging right along. Bring this back down. So we have our r vector, the magnitude of it. Now we're going to need r hat. So this is going to be x minus s over 2, 0, 0, divided by the magnitude x minus s over 2, and this is equal to 1, 0, 0. So this, again, confirms our picture. We knew that this would be in the direction of the x-axis. So we can plug this in for E positive. So this is 1 over 4 pi epsilon naught q over the magnitude of r squared, so that's x minus s over 2 quantity squared, times r plus hat, which is 1, 0, 0. And if we were to write this in vector form, we would have 1 over 4 pi epsilon naught q over x minus s over 2 quantity squared, 0, 0. All right, so E plus done. Now we need to find E minus. And for that, we're going to need our r minus. So r minus is equal to x 0, 0 minus, in this case now with the origin being at the center, we're going to do minus s over 2, 0, 0. And so this is equal to x plus s over 2, 0, 0. And then the magnitude of r minus is just going to be x plus s over 2. And r hat minus is going to be 1, 0, 0. With the minus sign in this case coming from the negative charge, not the unit vector itself. All right, so E minus is equal to 1 over 4 pi epsilon naught minus q over x plus 2 quantity squared times 1, 0, 0. And in vector form, this is 1 over 4 pi epsilon naught minus q over x plus s over 2 quantity squared, 0, 0. Okay, so now that we have the two components of our electric field, E positive right there and E minus right here, we can sum them together using the superposition principle to get the electric field of the dipole on axis. Okay, so E1 or E net is equal to E plus E minus. This is equal to 1 over 4 pi epsilon naught q over x minus s over 2 quantity squared plus 1 over 4 pi epsilon naught minus q over x plus s over 2 quantity squared, 0, 0. All right, so at this point we want to go ahead and generalize the result. So instead of x, we're going to say r, where r is going to be just the distance between the dipole and the observation location on axis. And this is because you might have a dipole in y, or you might have it in z, or you may have it in two planes. And so we want a generalized formula. All right, and so x is going to go to r, and the direction depends on orientation. So this is on axis, so we can calculate the magnitude, and then we know if it's going to be in the positive or negative direction, depending on whether or not you're closer to the positive or negative end. If you're closer to the positive end, it's going to point away. If you're closer to the negative end, it's going to point towards the dipole. All right, so the magnitude of the electric field on axis for a dipole is equal to 1 over 4 pi epsilon naught q over r minus s over 2 quantity squared plus 1 over 4 pi epsilon naught minus q over r plus s over 2 quantity squared. This is equal to 1 over 4 pi epsilon naught q over 1 over r minus s over 2 quantity squared minus 1 over r plus s over 2 quantity squared, and this becomes 1 over 4 pi epsilon naught 2qsr over r minus s over 2 squared times r plus s over 2 quantity squared. And on your own, I want you to fill in the algebra and practice seeing how one equation becomes another equation. All right, so we can do an on-axis dipole. So now we want to look at a couple approximations. So this is a rather large equation. Let's see if there's some times where we can have a simpler expression that will be good enough for the purposes intended. So I'm going to rewrite this. 1 over 4 pi epsilon naught 2qsr over r minus s over 2 squared r plus s over 2 quantity squared. So if r is much, much larger than s, so this would become very, very tiny, then r minus s over 2 squared is approximately r plus s over 2 quantity squared, which is approximately r squared. And thus, the electric field on axis for when r is much, much bigger than s, which is often, becomes approximately 1 over 4 pi epsilon naught 2q s over r to the fourth. And if this doesn't make sense to you, you should prove it to yourself. And then, of course, this is 1 over 4 pi epsilon naught 2qs over r cubed. So this would be the approximation for the electric field on axis. And then once again, Q is the magnitude of charge. And S is the separation of charge. And R would be the distance from the center to the observation location. And on your own, you should just double check that this approximation makes sense to you. I mean, question everything. All right, so let's go ahead and do a quick example. So we have a HCl molecule, which is a dipole, and it has charge of positive E coming from the hydrogen ion and negative E coming from the chloride ion. And this is separated by 1 times 10 to the minus 10 meters. And so let's go ahead and draw a picture. So we've got plus E is here, minus E is here, and we're going to be observing from here. So 4 micrometers away. So we can see in this case that we are closer to the minus sign, so we know that E net is going to be in this direction, but it is sometimes still worth it to just quickly draw a picture just to confirm. And there we can see. And so let's go ahead and calculate the magnitude. Now in this case, we can see micrometers, so that's 10 to the 6. That's much, much larger than 10 to the minus 10, so we can use the approximation. So the electric field on axis is approximately 1 over 4 pi epsilon naught 2qs over r cubed. And this is equal to 9 times 10 to the 9 Newton meters squared over Coulomb squared times 2 times, so in this case we've got our charges being plus and minus E, so that's 1.6 times 10 to the minus 19 coulombs times the separation, so that's 1 times 10 to the minus 10 meters, divided by 4 times 10 to the minus 6 meters quantity cubed. And so the magnitude of the electric field on axis is equal to 0.0045 newtons per coulomb. And if you have a question about whether or not this approximation is acceptable, go ahead and on your own calculate this using the more precise formula and prove to yourself that this approximation is appropriate. So we can see the negative end is closer. So the electric field points towards the dipole. So we can write this as a vector 0.0045 newtons per coulomb. We can see towards the dipole is in the positive y direction. It's pointing up. All right, so moving on, we can look at the derivation for a dipole along the perpendicular axis. All right, so in this case, we would have, say, a negative here, a positive here. We're going to be looking perpendicular to some point. Okay, so let's go ahead and draw some vectors. Once again, we've got our separation of the dipole of S. And so this is in Y. All right, so R minus is going to go from the negative charge to our observation location, and R positive is going to go from our positive charge to our observation location. So let's think about these fields. So E minus is going to point along this vector towards the charge. E positive would just continue this in that direction. If we were to add them together, we can see E net will go along right here. So already, without doing a single calculation, we know several things about what we can expect to find in our results. All right, so we need an equation though. So let's break this down. All right, we'll find, so once again, we want to find R positive and R negative. R positive is going to be, and so this is Y, is going to be 0, Y, 0, minus S over 2. So once again, the middle is in 0, 0, 0. S over 2, 0, 0. So our positive vector is equal to minus S over 2, y, 0. And our negative is equal to 0, y, 0, minus S over 2, 0, 0. And so our minus is equal to S over 2, y, and 0. Okay, so we know the magnitude of these two vectors is equal to each other. We can just see this with a calculation or a quick visual inspection or just what makes logical sense. So let's keep going. R positive is equal to our magnitude positive minus S over 2 quantity squared plus y squared plus 0 squared is equal to the square root of S over 2 quantity squared plus y squared. Our minus is equal to S over 2 quantity squared plus y squared, since we already said the two magnitudes are equal to each other. The unit vector r plus is equal to minus S over 2 y 0 over S over 2 quantity squared plus y squared taken to the power of 1/2, and our minus is just S over 2 y 0. Once again, we have S over 2 quantity squared plus y squared taken to the power of 1/2 for that square root. And so the electric field from the positive charge is 1 over 4 pi epsilon naught q over S over 2 squared plus y squared times minus S over 2 y 0 over S over 2 squared plus y squared taken to the power of 1/2. And we can do the same for the electric field from the negative charge. 1 over 4 pi epsilon naught minus q over S over 2 squared plus y squared times minus S or plus S over 2 y 0 divided by S over 2 squared plus y squared taken to the power of 1/2. And so our net field is going to be the sum of the positive and negative contributions and so our net is equal to 1 over 4 pi epsilon naught q times S divided by S over 2 squared plus y squared to the 3/2 minus 1, 0, 0. And we can see the y components cancel. And E net is horizontal and to the left, just as we predicted. Okay, we can go ahead and generalize. So we're going to replace y with r, and we can get that E perpendicular is 1 over 4 pi epsilon naught qs over S over 2 squared plus r squared taken to the power of 3/2. And if r is much, much larger than S, we get E perpendicular is approximately 1 over 4 pi epsilon naught qs over r cubed. And you can determine direction by visual inspection. right, we'll stop here and finish 13.6 in the next segment.